Assalamu alaikum. Dear students, today we will learn DC-DC converters. DC-DC converters are the electronic circuits that convert a DC voltage to a different DC voltage level. The circuits described in this chapter are classified as switched mode DC-DC converters, also known as DC chopper circuits. Uh, as you remember in chapter number 1, we studied an example of linear voltage regulator. If you recall that example, what we need to do at that time was to appear a voltage V out equals to IL into RL for a given input voltage. Let us revise this example. Uh, if you can recall in chapter 1, we had this Vs equals to 12 volt and our objective was to appear a voltage at an output voltage V out across the load resistor RL equal to 4 volt. To perform this task, we can use a variable resistor as shown in the figure. But if we do so, what happens that we need a variable resistor of 2RL to basically consume 8 volts out of the 12 volts that are being provided by the input voltage Vs. In this way, we can easily make the output voltage equals to 4 volts. But what happens that we basically lose 66% of the power. Uh, this scheme can be performed using a BJT. In the figure on the left hand side, you can see that we can use this bipolar junction transistor as an amplifier in its linear amplification region. So if we use that amplifier in the linear amplification region, we will consume 8 volts in this amplifier and hence we can get 4 volts across the load resistor RL. How can we perform this task? We can control the input current IB of the voltage, IB of this BJT, and hence it can produce the desired IC, the desired collector current, which is basically equal to the load current in this case. But again, if we will be using this BJT in its amplification region as an amplifier and we will be basically controlling its output current to get an output voltage of 4 volts, again we will lose 66% of the power that is being supplied to the load. So this is not a feasible thing to do. So what is the remedy of this problem? So we will be using uh, a converter. What this converter will do, you can see this figure, that is figure 6.2a. Again, there is an amplifier, there is a transistor BJT that is being used in the same place. But the difference in this diagram is that we are not using this BJT as an amplifier. Rather, we are using this BJT as a switch. So now either it will be operated in its saturation region or it will be operated in its cutoff region. So if the BJT is operated in its saturated region, it will be considered as the switch is closed. And what will happen that if the switch is closed, then the voltage across this switch is zero, and hence the output voltage is equals to the input voltage Vs. In the C diagram, you can see that for a time dt, the switch is closed and we are getting the output voltage V out equals to Vs for that time. Now, if the switch is open, then the voltage across the RL resistor is zero. So hence, what we are doing, we are providing the output voltage either as Vs for dt time and as 0 for the t time. Now, as an ideal switch, this BJT is not consuming any power. If the switch is closed, then the voltage across the switch is 0 and hence power consumed is 0. If the switch is open, then the current through this switch is 0 and hence again the power consumed by the switch is 0. So what we can say that in an uh, in a converter we make use of switching to achieve a desired output voltage. Now what happens if we uh, calculate the average power, average voltage? So we will integrate the waveform in this figure C for unit time period, that is from 0 to t seconds, capital T seconds. So if we integrate this waveform, we get output voltage V out as equals to Vs into D, where D is the duty cycle. What is the duty cycle? It is basically represented by equation 6.2, which means that duty cycle is the proportion of time for which the switch is closed for a unit time period. If the time period is, say, 1 second and the switch is closed for, say, 1 by 3 seconds, then the duty cycle is basically 1 by 3. Coming to the basic buck converter, that is a DC-DC converter that steps down the voltage from a higher voltage level. So this is the basic configuration of a buck converter. What happens that when the switch is closed, so you can imagine that the diode is reverse biased, so it will react as an open circuit, while the current will pass through the inductor and the AC component will be passing through the capacitor, while the DC component of the current will pass through the resistor where voltage V out is mentioned. So in order to uh, have a detailed insight of this circuit, we can uh, perform some assumptions. So what are those assumptions? Those assumptions are basically that the inductor current is periodic, which is represented by equation 6.3. Similarly, we assume that the average inductor voltage is 0. The third assumption is the average capacitor current is 0. And the fourth assumption is that the power supplied by the source is the power delivered to the load. And if there are losses, then power supplied is equals to power output plus the losses. That is, the supplied power will also compensate for the losses that are being faced. Another assumption is that the circuit is operating in its steady state rather than the transient situation. And very important assumption that the inductor current is continuous. What does it mean? Inductor current continuous means that it will never be less than 0. So if the minimum inductor current uh, is greater than 0, then we will say that the DC-DC converter is operating in its continuous conduction mode. Similarly, we assume that capacitor is very large, and the output voltage is held constant. That is, voltage V out is constant. And again, as shown in the figure, the switching time period is capital T, where switch is closed for the time dt and it is open for the time 1 minus d times t. We assume that all the components are ideal, including the switches, that are assumed as ideal. Now, if the switch is closed, so the circuit will behave like figure 6.3b being displayed in our screen. You can see that when the switch is closed, the diode is open circuited. Now if we apply KVL on the outer loop, we can write minus Vs plus VL plus Vout equals to 0. And it will give us VL equals to Vs minus Vout. Now, if VL is equals to Vs minus Vout, from basic elementary electrical engineering, we know that VL equals to LdI by dt. So if we divide this L on the other side of the equation, we can write that di by dt equals to Vs minus Vout upon L. Hence, we conclude that the rate of change of current is basically equals to the difference between the input and the output voltage divided by the value of the inductance. Now, if di by dt is basically change in current divided by change in time, then we can say that the change in current is basically equals to change in inductor current, that is delta IL, while the time for which this changes current is happening is basically the time for which the switch is closed, that is dt. Hence, we can conclude that delta IL for the switch closed is equals to Vs minus Vout whole divided by L times dt. Now, these are the figures that we will get when we will operate this buck converter in the switch closed mode. You can see that for the switch closed, the output voltage is Vs minus Vout. And the change in inductor current, that is delta IL, you can see that it is in between I minimum and I maximum. Now coming to the second part of this DC-DC converter, that is the case when the switch is open. So you can easily analyze this figure that when the switch is open, obviously the inductor current requires a path where it can flow. So what happens that the diode becomes forward bias and hence the inductor current can circulate from inductor through resistor and then back to inductor. Now again, if we apply KVL on this outer loop other than the source voltage loop, we can write 0 plus VL plus Vout equals to 0. And hence we get an answer that is VL equals to minus Vout. Again, since VL is the inductor voltage, and we know that from elementary electrical engineering, VL is LdI by dt. So we can write minus Vout upon L equals to di by dt. Now again, if we treat del I as delta IL and del T as 1 minus T into capital T, then we can write that delta IL open is minus Vout upon L times 1 minus D into T. So again, if you can see in this figure that again the inductor current is fluctuating between I minimum and I maximum, and the total fluctuation is basically delta IL for the switch is open. Okay. Now coming to the derivation of the output voltage, what we can do, we can say that the sum of the delta IL closed and delta IL is equals to 0, because these two currents are basically cancelling each other. So what happens that if we put the corresponding equivalent expression for this thing and simplify it for V out, we get Vs into D. So the conclusion is the conclusion is that for a buck converter, output voltage V out is equals to supply voltage times the duty cycle D. Now we can well imagine that duty cycle D is often between 0 and 1. So suppose if the duty cycle is zero point 0.5, then we can say that the output voltage is half of the input voltage. So you can easily analyze that in a buck converter, output voltage is most of the times less than the input voltage, and the maximum value of the output voltage is the input voltage. So hence we conclude that for a buck converter, output voltage is either equivalent to the input voltage or it is less than the input voltage. Now to uh, prove this thing in another way, what we can do, we can calculate the voltage of the inductor for the time when the switch is closed and for the time when the switch is open. So in this expression, VL equals to Vs minus V out is basically the voltage when the switch was closed. So Vs minus V out into dt, dt is the time when the switch is closed, plus minus V out, which is basically the voltage when the switch is open, into 1 minus d time capital T is basically the time when the switch is open. So if again we will simplify this expression for output voltage V out, we will get the same result, that is V out equals to Vs into D. So the conclusion is same, that in a buck converter, either output voltage is equal to the supply voltage or it is less than the supply voltage. Now, as the DC current is flowing through IL and IR, and the DC current is basically same because the inductor and the resistor in a buck converter configuration are in series. So we can say that IL can be represented by IR and it is equals to output voltage divided by the load resistor. Now coming to the expressions for the maximum and the minimum current, as we can see in the previous figure, let me just open the figure for you. This is the figure. So for this figure, suppose we are taking this point, so we can say that basically the maximum current is equal to the current IL plus delta IL upon 2, because you can well imagine that the current that is above the dotted line is basically the current delta IL whole divided by 2. So keeping this figure in mind, we can see that I maximum is IL plus delta IL upon 2. Hence, if we put the expression of delta IL in this equation, we get the expression that I maximum is V out times 1 upon R plus 1 minus D upon 2LF. Similarly, for I minimum, we can see that IL minus delta IL upon 2 is equals to I minimum. And hence we conclude that I minimum is equals to V out into 1 upon R minus 1 minus D upon 2LF. Now, if we replace the frequency uh, with 1 upon T, so we can write the expression that is represented by equation 6.12. Now coming to another fact, that we know that a buck converter is usually operated in its continuous conduction mode. So to meet this condition, we can take I minimum is equals to 0. So when we do so, what happens that we get an expression for inductor. Now this inductor expression is basically predicting that what is the minimum value of inductance that we can use for a buck converter that is operating in its continuous conduction mode. So in the design process, we will use this formula to calculate the minimum value for which the buck to buck for which the DC-DC converter, that is the buck converter, is operating in its continuous conduction mode. Similarly, an expression can be derived using equation 6.15 and 6.16, and hence we can write that L is represented by Vs minus V out upon delta ILF into duty cycle D. So all these expressions are basically to find out the value of minimum inductance that can provide a continuous conduction mode operation. Now coming to the last derivation of buck converter. Buck converters are also known as DC transformers. Why is this so? Because if you uh, consider this equation 6.17, you can easily compare it with a transformer equation where V out upon Vs is equals to Is upon I out. So this equation is valid for an AC transformer, and at the same time, this equation is valid for a DC-DC converter, that is a buck converter. So we can say that it is a DC transformer. Now coming to the ripple voltage expressions, as we know that from the basic configuration of buck converter, if we apply KCL, we get to the conclusion that IC is equals to IL minus IR. Now, uh, we know that uh, the charge is basically capacitance time, basically equal to capacitance time, the output voltage. So for a small charge, we can write this equation as del Q equals to C times del V. Now del V is basically the ripple voltage. So we can say that del V, that is the ripple voltage, is equals to del Q upon the capacitance. Now, if we consider this figure, that is figure 6.5a, this del Q can be calculated by calculating the area of this triangle. So as we know that the area of triangle is equals to half into base into height. So we can easily conclude that the base is t upon 2 while the height is delta IL upon 2. So if we multiply half by t by 2 by delta IL by 2, we conclude that delta Q equals to t time delta IL upon 8, and hence delta V naught is equals to T times delta IL upon 8C. And again, from this expression, what we can do, we can basically find a value of percentage ripple, that is delta V naught upon V naught, uh, which is represented by equation 6.19. Now, from this 6.19 equation, if we make C the subject of the equation, we can easily find the value of capacitance for a specified or for a particular percentage ripple that are being allowed to us. So this was all about the buck converter configuration. The conclusion is that buck converters are the DC-DC converters that convert a higher DC voltage to a lower DC voltage. And when the buck converter is in continuous conduction mode and the switch is closed, the output voltage is Vs minus V out. And when the buck converter is switched off mode, sorry, then what happens that the output voltage is equals to minus Vs. And finally, if we find an expression for the output voltage of the buck converter, it is V out equals to Vs times the duty cycle, where duty cycle is basically the time out of a unit time period for which the switch was closed. Using the continuous conduction mode condition and the ripple percentage ripple limitations, we can find uh, minimum values of inductance and capacitance that may be used to design a buck converter. So inshallah, in the next class, we will discuss with you some numericals, uh, and we will basically discuss with you the design of buck converter. Thank you.